Okay, students. Now the second theorem second to the Thevenin's theorem is the Norton theorem. So it is very similar to the Thevenin theorem. So Norton and Thevenin theorem are basically equivalent of each other as well. So if you see, Norton theorem says what, that if you have a linear two terminal circuit like this one, right? Okay, so you can represent this by a current source, which we call it an I Norton, and a resistance in parallel, which is Rn. So Rn is basically a Norton resistance. Okay, now remember, previously we said that any linear two terminal circuits can be represented by a Thevenin voltage, which is V Thevenin, and in series with R Thevenin, like this one, and then we have the AB. So if you see this Thevenin circuit and Norton theorems, they are the same. They follow the same concept as we studied in the source transformation last time. So basically, how to find then Rn, the Norton resistance. The Norton resistance can be calculated exactly in the same way as we calculated the R Thevenin, right? Okay, so remember, R Thevenin was Rn when you make this terminals open, and then you actually determine the total R input, which is equal to the R Thevenin. So it is actually the R Norton as well, right? Okay, so and how can we determine this IN, which is the current? Now remember this current, how can we find this current? This current can be determined by using a short circuit. So if you make, okay, this A and B, between A and B you put a short circuit, so you can actually calculate then IN. Okay, so this is the Norton current. Remember, this is just opposite to the Thevenin voltage, where you make this open. So over here you make it close, right? Okay, so we will do a short example. So let's do this example which says 4.11. So 4.11, it says that for the Norton circuit in the figure 4.39, okay, so find the equivalent Norton circuit for the given circuit. So it means that I can represent this, okay, by a Norton circuit, which is I current, and in parallel with a resistance which is we call Rn, and this is In, right, and this is the terminal. So to find this Rn, okay, so remember, to find this Rn, so last time we said to find this is equivalent to R Thevenin. So the same way we found R Thevenin. So what we would make, we would make two assumptions, okay, apply two rules. The voltage, okay, sources should be short circuited, and the current sources should be, okay, current, if you have current in the ground, it should be open circuited, right? So if it is like this, so how many voltage source we have? We have this. How many current source we have? We have 2 ampere. So from A, if I go, right, this is my A. From A, if I go, then I have 8 ohm resistance, okay, then I have 4 ohm resistance over here. Between this I have the source, so I'll make it short, right, and then okay, I have a resistance which is also 5, and then if you see, I would neglect this part, okay, so I don't or not extend the circuit. Okay, the circuit looks like this, right? So, and remember, we have another resistance which is 8 ohms, which is over here, right? So basically the circuits is, okay, if you see this over here, I can redraw. So this is 5, which is this one, and this branch has 8 in series with 4 in series with 8 again. So basically I represent this by a single resistance, and this is how this is AB, this is and this is 8 plus 8 plus 4. So basically this would be to 8 16, this is equal to 20 ohms. So this is 20 ohms resistance. Now the equivalent of 5 and 20, so we know that this would be R1 R2 divided by R1 plus R2. So basically I can write this 20 into 5 divided by 25, okay, so 5 5 5 4. So basically you have this is resistance is equal to 4 ohms. So it means that Rn is now 4 ohms. What about In? In would be, to in order to evaluate In, I would short circuit these two terminals, right, in the circuit. Okay, so remember, to do that, okay, my circuit becomes what? This is 2 ampere current, then I have 4 ampere. Okay, then remember this voltage source, I would write this as it is. Okay, I cannot remove now. This is 12 volts. Okay, then I have 8 ohm resistance, right, and then I have 5 ohms resistance over here. Okay, and then I have a short circuit like this one, right. So it means that if I have a short circuit, okay, so okay, what do you think? Okay, according to definition, if you have a parallel short circuit with a resistor, so this resistor can be ignored, right, and this circuit can be, we can rewrite, we can redraw over here as what, as 2 ampere. So basically this is 2 ampere. Okay, and then the 4 ohm resistor, and then the source which is 12 volts, right. So basically, sorry, I can, sorry, redraw this as this is a source which is like this. It has a value of 2 ampere, then I have 4 ohms, and then if you see, this is plus minus, okay, 12 volts, right, and this is now 8, right, over here. Okay, okay, remember, this is 8 as well over here. This branch is only over here. I have 8. Okay, so this branch would be removed, and then I have a short circuit like this one. Okay, students, to find okay, so to find now the Rn, we calculated, it comes out to be 4 ohms, right. Okay, so basically this was, if you see, sorry, this was In, right, and then the Norton equivalent circuit of the given circuit in figure 2.4.11, this was Rn, so it comes out to be 4 ohms, right. Now to calculate In, so we need to short circuit these two ends. Okay, when we short circuit, so by definition, okay, when this parallel branch, which is 5 ohm resistance, parallel with the short circuit, so we can ignore, okay, the current would go directly in the short circuit. Okay, so there will be no current flowing in the 5 ohm resistance, right. So we have to redraw this diagram again, this circuit again. So for that, I can redraw over here. I can say this is my 2 ampere, then I have this 4 ohm resistance. Okay, then you have plus minus this 12 volts, right, and then it is connected. Okay, if you see 8 ohms over here, okay, 8 ohms, and then you have 8 ohms over here, 8 ohms over here. So we ignore the 5 ohms, and then from the terminals A and B, I can make it a short circuit like this, right. So this is what, this is In, right. So it means the current, to find the current In, so somehow if I find the current in this branch over here, okay, so it would be in this loop, it would be my In actually, right, it would be my In. So I can apply mesh analysis. I can say M1, so this is current I1. I can apply mesh 2 over here, this is I2. So you can see in the book he has solved using this as a mesh, right. Okay, as mesh, you can see over here, you can find this as mesh. Okay, so but we can also solve this circuit using nodal analysis, okay, and using also source transformation method. So if I find, let's suppose if I do it with respect to by source transformation, if I find this current somehow by source transformation, so what can I find? That I can convert this 12 ohm resistance on volt source, which is connected in series with the 4 ohms. So I can convert this into a voltage source, a current source, sorry, this voltage source is converted into a current with the positive end like this, right. Okay, 8 heading towards the positive terminal of the battery actually. And then I can put this as 4 ohms resistance, okay, over here. Then this 8 ohms resistance is 8 is as it is. Then I have, right, the short circuit, okay, and then I have, right, the 8 ohms resistance again, and then I have, right, okay, and then this source, okay, which was equal to 2 amperes, okay, it would be like this thing. So I can connect it. Now what should be the value of this source? So this is I equal to V divided by R. So V is 12 and R is 4. So basically this is equal to 3 ampere. So it means that I have 3 ampere over here. Now collectively the net current over here in this node, if you see, the circuit is 2 and plus this 3 ampere. So basically you can add this up. So the equivalent circuit, if I draw it over here, it would be, okay, it would look like this, okay. I would have a current which have a value of 5 ampere. Then I would have, okay, a source of value of 4 ohm resistance. Then I have 8 ohm resistance again over here, and then I have 8 ohm resistance like this thing, right. This is also 8 ohm resistance, right. So if you see now, again I can use a source transformation method. So I can convert this into a voltage source. So to convert into a voltage source, okay, I would have a voltage source with the plus over here, minus over here, because plus is at the upper portion, okay. And then what else I would have, okay, I would have this 4 ohms 4 resistance connected now in series, okay. And then if you see, I have this 8, and then I have it again. So basically this is a circuit now. Value of this is 8 again. The value of this voltage can be determined using V equal to IR. What is I? It is 5. What is R? Which is 4. So basically this is 20. So this is 20, right. So it means that uh, I can, if I apply a KVL over here in this loop, so it will be minus 20 equals to, okay, or minus 20 plus 4i, then plus 8i plus 8i equal to 0. So basically if you see okay, now if you see, the total current would be minus 20 equals to minus 8 plus 8 16 20 I, right. So this cancels with this. It means I is equal to 1 ampere, right. So it means that this value has a value of 1 ampere. This I is also equal to your nodal current, which is IN. So this is how you perform the Norton analysis. Thank you. Okay students, now we will try to solve this practice problem, which is basically 4.11. It says find the Norton equivalent circuit of the given circuit, okay. So we need to find the Norton equivalent circuit. So Norton equivalent circuit, by definition, it is represented by a current which is IN, okay, Norton current in parallel with a resistance which is R Norton, okay. And then we have the terminal A and B. So this is equal. Now we need to find this Rn. So Rn is exactly the same way we found R Thevenin. So for that, what we will do, we apply two rules actually. We will make this open as it is, okay. The circuit is already open, okay, from the terminals. And then we apply any voltage, we short circuit voltage sources, and we if there is any current sources, we make it open circuit, right. So this given circuit I can redraw as from a terminal A. If I go, I have the resistance which is 3, okay, this is 3 ohms, okay. And then I have a resistance which is 6, okay. So this is okay. Now I open this, so I don't need this thing, okay, I ignore. Then I have the 3 ohms branch, okay, and then I have a short circuit from this 15 ohms from source can be made as a short circuit. So basically if you see, this is how my circuit would looks like. So basically if you see uh, the 3 plus 3 again, these three resistances, two resistance of each of value having 3 ohms can be connected in series. So I can redraw this as from, okay, this is 6 ohms resistance, this is the point where you have A, this is B, okay, and then over here this is, I can add them up, these two resistances, I can say this is 6, so 6 is over here, right, this 6 over here, right. Now this is in parallel, 6 is in parallel to 6, so the equivalent resistance would be 3 ohms, right, if you apply that formula. So it means that Rn is equal to 3 ohms, right. You can see the answer is 3 ohms. Now to find the value of In, this one, okay, we have need to redraw the circuit again. Okay, if I redraw the circuit again, and I would make this as a short circuit over here, so this will be my In. So if I made a short circuit, so by definition, okay, this 6 ohm resistor is in parallel, so it would disappear, right. So my circuit would become what? My circuit would become plus minus 15, okay, then I have 3 ohms, right, okay, then I have uh, basically a current which is 4 ampere, right, and then I have again a 3 ohm, and then, okay, I will neglect this 6, this is short circuit which is In. Now I can, once I find this current in this branch, okay, so either using mesh, okay, so let's suppose I2 and I1, or using nodal analysis, so that would be my, the current in this loop of branch would be my In. I can also use source transformation. Now to use source transformation, basically how can I work? Okay, basically uh, I can do like this. Over here, a 15 volt source and 3, okay, I can convert this into our current source. So basically if I convert into a current source, so it means that this is my current with direction, with is a positive terminal over here. This 3 ohm resistor would be connected, would be shifted to in parallel. Then I have, okay, this current which is having a value of 4 ohm, and then 3, okay, and this is my circuit now, which is, this is 3, okay. What is the value of this? This is I equal to V divided by R, V equal to 15, I equal to 3, so the value is 5, so this is 5 ampere, okay, and this is already 4 ampere. So you can see this 5 and plus 4 ampere, okay, they are in actually they add in this node, right. So basically I can redraw this circuit. I can say that this is equal to 5 plus 4 is 9 ampere, okay, and then this 3 which is over here, okay, and then I have this 3 again over here in this branch. This is my circuit, this is 3. Now, okay, and this is what the circuit I was interested, which is my In. So it means that 9 ohms, 9 ampere current goes over here, okay, so it is get distributed, divided in this branch, in this branch. So I can apply current divided rule, okay, to find this current. So it would be, let's suppose I would say current in the third branch, this is equal to the total current which is 9 into, right, into uh, the resistance of the opposite branch divided by 6, right. So basically if I, okay, so this will be 326 and this is 4.5, so I3 is equal to In, which is equal to 4.5 amperes. It means this is the current over here is 4.5 amperes, right. Okay, so remember this will also equal to 4.5 amperes. Why? Because these two are resistances are equal. So it means that okay, that this IN is equal to 4.5 ampere. And if you check it, that is again the same thing as given in the answer. Thank you.